Now we're going to talk about measures of quality for generative adversarial networks. Could you please tell me if these images are real or fake? Some of them are quite realistic, aren't they? And yes, you're right, they are all generated. But how about these images? Do you think any of these images real? Or all of them are fake? And if you pause the video, you could mention that despite the very good quality of these faces, some hair are like plastic. And yes, all these images are fake. I'm not going to ask you about these images. They are all synthetic. Looks quite nice, right? So how you define if the image is good or not? How do you know if the image is close to the real samples or not? Well, you have a neural network in your head, but how we could measure the quality of generated images? Is it possible? And the answer is yes, and we will study how to do it. So, why do we need the measure of quality for GANs? Firstly, we should have some way to compare different models with different hyperparameters, such as number of layers, layer types, and number of parameters. Secondly, when we train GANs, we should have an indicator of quality in order to stop training in the right time. Last but not the least, if we write a research paper, we should somehow compare our model with existing. It is very bad practice to say, our generated cat is better than others, without providing any numerical comparison. We want our measure of quality to correlate with two aspects. First, what is the quality of our synthetic images? How good are they? And second, how diverse is our generated set? Does it cover all image classes, or it generates only one image each time? The second metrics requirement is very important. When training GANs, there exists a problem of mode collapse. Look at the top image on the slide. Our target distribution is a mixture of Gaussians, which you can see on the right. It has several modes, but at different epochs of training, our GANs model will generate samples only from one mode, but not from all of them as we expected. This is what people call mode collapse. Considering images, if we train our model on Mniz dataset, the mode collapse will be if the model starts generating only one digit. That is why it is important that our measure of quality could manage this. As I said a few slides ago, our brain has a neural network that decides whether the image is real or fake. The methods that people use for distinguishing real and fake images also use their own network. It is called the inception network, also known as GoogleNet. It was trained on the ImageNet dataset, which consists of around 40 million of images of 1000 classes, such as dogs, cats, mushrooms, airplanes, and so on. Let me briefly remind you what is entropy of the distribution. The entropy is a measure of randomness of the distribution. It means that the more the distribution is uniform, the higher will be the entropy. And vice versa. If the distribution is concentrated in one point, it will have the smallest entropy 0. As you can see on the slide, the entropy of P2 distribution will be higher since it is uniform. The distribution P1 is more concentrated. The first measure of quality is inception score. Firstly, we used inception network for predicting the distribution P of y given x. This is an output of the last softmax layer of the inception network. We want this distribution to be highly predictable. In other words, we want it to be concentrated in one point. It means that we want the entropy of this distribution to be lower. And this stands for the quality of an image. The more concentrated is our image, the more confident is the network in the prediction, which is good in terms of the image quality. Okay, we understood that we want the entropy of the distribution P of y given x to be lower, and it stands for image quality. Now we have to do something with image diversity. For this reason, we can consider P of y distribution. We want it to be uniform, which means that we want the entropy of P of y to be higher. Now, how to calculate P of y? We should generate a lot of images. For each of them, make a forward pass through the inception network and predict P of y given x. Then we need to average our prediction distribution by x, by our images. X is our images. Thus, we will obtain the distribution for P of y. Look at the picture on the slide. Here is the demonstration of our wishes. We want P of y to be uniform and P of y given x to be concentrated in one point. From the probability theory, we could remember that Kullback-Leibler divergence between two distributions is the difference between the cross entropy and the entropy. Taking into account the fact that we want the minimization of the first entropy and the maximization of the second entropy, we can combine them into a Kullback-Leibler divergence, and here we obtain inception score. It is defined as the KL divergence between two distributions, P of y given x and P of x. And now you know how it was obtained. Note that the higher the inception score, the better is our GANs model. Now let us discuss the second measure of quality for GANs, Fréchet inception distance. As you can guess, it also uses inception network, but in a different way. Firstly, we use inception network for feature extraction for both synthetic and real samples. Then we assume that the obtained features are distributed as a multivariate Gaussian distribution. Then we estimate their mean and covariance matrix. We do this both for real and synthetic images. Then we compute FID with the equation on the slide, as the difference of means and the trace of the square distance of covariance matrices. The lower Fréchet inception distance, the better is synthetic image quality. Fréchet inception distance was shown to be sensitive to mode collapse, which is good for us. When our generator sample images only from a subset of classes, the FID starts increasing. Let us now compare the inception score with Fréchet inception distance. Both of them correlate with human assessment. However, inception score doesn't take real samples into account at all. If our generator samples only one image per class, then the inception score will fail and show high score. FID is sensitive to it. The disadvantage of the FID is that if we take two different batches from the train set, then FID will be non-zero, which is not good. And both these two metrics have a common disadvantage. They can be applied only to photo-like images like cats, dogs, airplanes, or anything. If you generate specific images like MRI or textures or any medical data, then these methods are inapplicable. The last measure of quality that I would like to discuss is geometric score. It is based on the manifold hypothesis and applicable to any kind of data. If you want to use it, use the link to the GitHub from the slide. It is all for measures of quality. Thank you for watching and see you in the next video.